Welcome. This time I will show how the required performance of the vehicle will determine the requirements on the powertrain, and how the requirements can be illustrated as a required operating range in a force-speed diagram. Finally, I will also explain why performance requirements are a compromise between customer value and cost. The vehicle model tells us which properties we need to describe in order to know what force the powertrain must produce. We must specify the vehicle speed, vehicle acceleration, and road gradient. The first step is to specify the maximum value of these three, one by one. In our example, the maximum vehicle speed for this passenger car is 200 km per hour. It shall be capable of 4 meters per second square acceleration. For safety reasons, a vehicle should be capable of decelerating as much as the road friction allows, about -10 meters per second square, but since that force is provided by the brake system, it is not a part of the powertrain requirements. The road gradient is most of the time below 20%, but to handle extreme cases, our car shall be able to climb 30% gradients. This analysis only deals with the requirements when driving forward. Requirements for performance on reverse gear are different, but can be analyzed in the same way. Now we can use the vehicle model to calculate what operating points the requirements lead to, and then plot them in a force-speed diagram. We are not interested in each and every operating point, but rather the ones leading to the highest force at each speed. The maximum speed is the limit above which the powertrain does not need to generate any force. Driving at constant speed on a flat road means that the powertrain needs to produce a traction force equal to the running resistance. If we add the force required for acceleration, we get the green force limit, which shows the force required to accelerate 4 meters per second square on a flat road. We now analyze driving at constant speed up a 30% gradient, and then we get the brown force limit. Note that the force required for the gradient for this car is lower than the force required for acceleration. This should be no surprise, since 1 meter per second square acceleration requires the same force as 10% gradient. For this vehicle we required 4 meter per second square acceleration, but only 30% gradient. So of these two situations, the acceleration on flat road will be the one setting the highest requirement on the powertrain. It does not matter for the powertrain if acceleration or gradient is the reason for a certain force. Instead, we only need to know what is the highest force required at each speed. If we want the car to accelerate 4 meters per second square also while driving on a 30% gradient, we need to add both acceleration force and gradient force to the running resistance force. That requires a very high force, shown by this red limit. The maximum force requirement and maximum speed requirement are borders for the operating area within which the powertrain must be able to operate. The required operating area can be illustrated as the gray area in the diagram. But even if the driver may like to be able to operate in all these possible combinations of speed, acceleration, and gradients, it will be very expensive to design the powertrain to meet all possible operating points. For each requirement on the border of the operating range, there is a trade-off. For example, the cost for the powertrain might be significantly reduced if a requirement is reduced. And if the customer also doesn't see this performance requirement as a must-have, it might indeed be possible to reduce that requirement. The cost of the powertrain depends on several factors, and the required wheel force is one of them. The higher force is required, the more expensive the drive shafts and the gearbox becomes. Therefore, there is a good reason to reduce the force requirement if that does not make the vehicle less valuable. The first way to reduce the force requirement is to note that the steep uphill gradients are quite rare. Therefore, it may be reasonable to accept lower acceleration the short time the vehicle is driving uphill. Since the powertrain can accelerate 4 meters per second square on a flat road, the same force is capable of accelerating 3 meters per second square on a 10% gradient, 2 meters per second square on 20%, and 1 meters per second square on a 30% gradient. We assume that this acceleration performance on gradients is okay for the car we investigate here. To not require high acceleration on uphill gradient, significantly reduce the required powertrain operating area and reduce the cost. Note that if we increase the acceleration required on a flat road, the vehicle will automatically get better acceleration at gradients, and also the possibility to climb even steeper gradients. Of course, the cost for the powertrain is strongly related to the cost for the engine or electric motor. The more power, the higher cost. Therefore, the operating point which require high power should be analyzed to see if they are very important or if the requirement leading to them can be reduced. It is interesting to plot curves where each point on a curve give the same power value to see what operating points require high or low power. Since traction power equals traction force times speed, the force along these curves equals the power divided by the speed. All points along this line require 400 kilowatt traction power, and the points above the line require even higher power. Along this line the power is 200 kilowatt, and along this 100. We can see that it is only high force at high speed which require very high traction power. Changing requirement does not influence the rolling resistance and aerodynamic resistance of a given vehicle, but by accepting lower acceleration and lower gradient ability at high speed, the traction power demand can be reduced. For medium performance cars, it's often reasonable to have a maximum traction power of about 150 kilowatt. To limit the traction power to 150 kilowatt means that the required operating range is reduced to this area. We can see that the force at 4 meters per second square acceleration, the green line, cannot be met above 85 kilometers per hour, since that would require a higher power than 150 kilowatt. And driving in constant speed on a 30% gradient is not possible above 110 kilometers per hour, for the same reason. To accept that the vehicle cannot drive uphill a steep gradient at high speed is usually not a problem, since the speed limit is reduced on roads with high gradients. To reduce the requirement for acceleration at high speed is probably the compromise which is the most noticeable for the driver, since acceleration on motorways often occur. However, the 150 kilowatt traction power assumed allows this car to accelerate 3 meters per second square in 110 kilometers per hour, which should be considered as quite a good performance. In this video, we have learned that vehicle requirements describe the required combination of speed, acceleration, and road gradient. They can be translated into force speed requirements for the powertrain using the vehicle model. The vehicle requirements are a compromise between how valuable the buyer finds a certain requirement and the cost for meeting it. Two reasons to compromise are to avoid requirements which either lead to high traction power or lead to high traction force. Some ways to reduce powertrain cost are: reduce acceleration requirements in high speed, reduce gradient requirement in high speed, accept lower acceleration on gradients than on a flat road. You can now do some exercises to learn more about operating ranges for powertrains and consequences of reducing power and force of the powertrain.